In this video, I'm going to be going over current division. Now, current division is when you have one current source, such as the one I've listed here, that is supplying a bunch of elements that are in parallel. For example, this current here is splitting between three different resistors. And if you think about it intuitively, current is going to follow the path of least resistance. So it would make sense that this current that the majority of this current goes through the resistor out of these three that has the least resistance. And so I'm going to be writing out the formula for current division and showing you how to make it intuitive. And so I'm also going to write the requirements for current division on the board now. So the first thing is the components need to be supplied by a single current source, or you need to be able to identify a current source or a current that is flowing across components in parallel. So this is the main condition that you have to worry about. So components in parallel being supplied, or components in parallel, being supplied current. And so all that means is that the components that you're dividing the current among have to be in parallel, otherwise, or in other words, they have the same voltage across them. They're connected to the same two nodes, as I've shown here. So those are the requirements for current division. So I'm going to be going over the derivation for the formula now. So in this part of the video, I'm just going to be deriving the current division formula. And in order to do that, I've written out these two diagrams, which are equivalent. So I have a current source I that's applying current to R1, R2, and R3 with currents I1, I2, and I3. Now all three of these resistors have a voltage V across them, and that makes sense because they're all in parallel. And then I is being supplied here, as you can see. Now with the right diagram, I have a current source I that's supplying Req with the same voltage V across Req. And now this voltage is V because all I did was simplify R1, R2, and R3 by combining them in parallel. So Req is just equal to, I'll write it out, R1 parallel R2 parallel R3. And since the components are in parallel, the voltage across them is going to be the exact same. And so the first thing I'm going to do is I'm just going to write Ohm's law for the circuit on the right side. So in this case, I have a voltage V, resistor R, and a current I. So I'm just going to write that V equals I times Req. And now the next thing I want to do is I want to solve for one of these currents independent of the voltage that's being supplied across it. All I want in a problem or a circuit to analyze is just a current and then a bunch of resistors, and I want to be able to solve for the current through the resistor automatically without having to go through the voltage. And so in order to do that, all I'm going to do is I'm going to write out the equation for I1. It's arbitrary. I could do I2 or I3, but I'm just going to choose to do I1. So writing out Ohm's law, I have resistor R1, current I1, and then a voltage V with the plus here and the minus here. So I'm going to write out that V equals I1 times R1. And I stated earlier that I want to eliminate the voltage in this scenario. So all I'm going to do is take this V and plug it in here. So I get that I times Req equals I1 times R1. And the next thing I'm going to do is just solve for I1. So I1 is going to be equal to I times Req divided by R1. Now, if you notice something about this current division formula, the part inside the parentheses is just the reciprocal of the voltage division formula. Now I'm going to write out voltage division on this side. So now this formula for voltage division does not apply to this circuit. I'm just writing out the arbitrary formula. So I'm just going to say that Vn equals Vs, which represents the source, times Rn divided by Req, where I'm going to write out Req S. Reqs being resistors in series. So this is for a different, like an arbitrary circuit where resistors are in series. Now, one thing you'll notice is that the part inside the parentheses here says REQ divided by R1, where in this part it says Rn divided by REQS. And the reason for that is that, like I said earlier, current will follow the path of least resistance. So whichever of these resistors has the least resistance, the current supplied by the current source will follow that path. Now, that's seen pretty obviously in this formula here, because if R1 goes down, then this right-hand side of the equation is going to go up, and therefore your I1 is going to be higher. Now, if R1 increases, the right-hand side of the equation is going to decrease, so I1 will decrease. Now, with voltage division, you know that V and R, or V equals IR, V and R are directly proportional. So if R goes up, V will also go up. So if the resistance you're looking at is increasing, which you see up here, Rn is just an arbitrary resistor, your Vn across that resistor will also increase. So I hope this was intuitive. The next thing I'm going to do is I'm actually going to solve this entire circuit using conductances so that you can see another intuitive way to think about current division. Now, the next thing I'm going to be doing in this video is just going over the current division formula derivation, but with conductances instead of resistances. Now, before I get into that, I'm just going to have a brief review of conductance. So conductance is just the reciprocal of resistance. So if my resistance goes down, the conductance goes up. And if the resistance goes up, the conductance goes down. So if I wanted to rewrite Ohm's law, I could do the following. So V equals IR, R equals 1 over G. So I'll plug that in. So V equals I divided by G. And so the most useful case, or one of the more useful cases for conductance, is combining resistors in parallel. So if you remember the formula for resistors in parallel, you get R1 parallel R2 parallel R3. That equals 1 over R1 plus 1 over R2 plus 1 over R3, all of that to the power of -1. And that equals REQ. Now, if I wanted to write that out in a different way, I could write out that 1 over REQ equals 1 over R1 plus 1 over R2 plus 1 over R3. Now, I can replace each one of these with the corresponding conductance. So I get that GEQ equals G1 plus G2 plus G3. And you can imagine how adding conductances can be a lot simpler algebraically than taking the inverse of each one of these elements and trying to do this negative to the power of -1, like the inverse operation. And so that's why I could just simplify G1, G2, G3 to this GEQ by just adding the conductances. So I hope that helped you understand conductance. So I'm going to be going over the current division formula, but using conductances. So the next thing I'm going to be doing is deriving the current division formula using conductances. And to do that, I'm just going to write out Ohm's law for the circuit on the left. So I have a voltage V, current I through this entire circuit, and a conductance GEQ. So using Ohm's law, I'll write out that V equals I divided by GEQ. And let's say I wanted to solve for the current I1. Again, this is arbitrary. I could solve for I2 or I3. I'm just choosing to solve for I1. And to do that, I'm just going to write out Ohm's law again. So I have a voltage V across the resistor, conductance G1, and a current I1. So I'll write out that V equals I1 divided by G1. And again, I want to be able to solve for values in my circuit independent of the voltage across these components. That's just following the main reason we use current division. So I'm just going to replace this with the V here. I'm just eliminating the variable V. So I get I1 divided by G1 equals I divided by GEQ. And again, I'm solving for I1. So I get that I1 equals I times G1 divided by GEQ. So this is my formula for current division for this particular circuit. And if I wanted to write out this, if I wanted to expand this formula, I'll get the following. I'll get that I1 equals I, which is just the source current, times G1 divided by G1 plus G2 plus G3. Because that's just the expansion of GEQ, because I just added the conductances in parallel. And so I hope this helped you understand current division. The next thing I'm going to be doing is going over the general form for current division using both resistances and conductances. In this part of the video, I'm just going to generalize the formulas for voltage or for current division for both of these circuits here, because I talked about writing out the formula for using both conductances and resistances. So for the circuit on the left, IN, which is just a current through a resistor Rn of a bunch of resistors in parallel, it's going to equal, so IN equals your source current, which is I, times all of your resistance or your equivalent resistance, so R1 parallel R2 parallel all the way to Rn, divided by your Rn. And this formula makes sense, just like I said before, because if Rn goes up, if your resistor's resistance goes up, less current is going to flow through it because your current is going to take the path of least resistance. Now, your formula for the general current division for using conductances is just going to be the reciprocal of this, but with a little change. So I'm just going to circle this. So for this circuit here, IN is going to be equal to your source current again, multiplied by the conductance you're looking at, so G sub N, divided by all of your conductances added together. Because remember, if you are taking parallel resistors and using their conductances to combine them, you just add their conductances. So G1 plus G2 plus all the way to Gn. And again, this formula also makes intuitive sense because if your conductance Gn goes up, that means that your resistor is more conductive and more current is going to flow through it. So I hope generalizing the formulas made sense. The next thing I'm going to do is go over a little bit of my own intuition for using current division. So the next thing I'm going to do is try to make the formulas for voltage and current division a little bit more intuitive. So I wrote out the formula for current division here, where I have a current source supplying all these resistors in parallel. And the formula is, for IN at least, it's just the source current times your conductance Gn of the resistor you're looking at, divided by all of your conductances added together. And for voltage division, all you do is you look at the voltage that's across all of the resistors, V, and then you multiply that by Rn, which is the resistor you're looking at, divided by all the resistors in series, and that's just to find Vn, which is the voltage across the resistor you're looking for. And one thing you can notice is that there's a lot of similarities between these two formulas. You have your IN, which is the current you're trying to find, Vn, which is the voltage you're trying to find, and that equals your source current, your source voltage in this case, times the conductance that you're looking at. Now this is a resistor you're looking at, divided by the sum of all these conductances in this case, and the sum of all these resistors in this case. So the way I'm going to try to make it intuitive is I like to think about it in terms of proportions. So the first thing I like to do is I'm going to start with the left side. Find your source current. In this particular case, my source current is just this current source I. I'm going to do the same thing on the right side, but I'm going to find my voltage across series resistors. And that just means I'm just going to put my hand where the chain of resistors starts and it ends, and I'm going to try to see if there's one single voltage that's applied across all of them. And I'm just going to label my ground node. In this case, the voltage that's applied across all the resistors is just V. So if you find your source current and find your voltage across your series of resistors, you already have one part of your equation. And now the next thing I'm going to do is find proportion of the total conductance that the resistor takes up. And what I mean by proportion is I just take my conductance and I divide it by the sum of all conductances. So I'm just trying to find the proportion of the conductance that this resistor takes up out of all the resistors. And I'm going to do the same thing on the right side. except I'm going to find proportion of total resistance that my resistor takes. And you can see that because I'm just taking my resistor, which is Rn, and I'm dividing it by the sum of all resistors, which is R1 plus R2 all the way to Rn. And the last thing I'm going to do is I'm just going to multiply So the third step is just multiply 1 and 2. And this is the same for both scenarios. Multiply 1 and 2. So just to recap, with both voltage and current division, current using conductance and voltage using resistance, I find my source, I find my supply current in this case, voltage in this case. I find the proportion of the total conductance that this resistor takes up, which is, using conductance in this case, using resistance in this case. And then I just multiply the source and then the proportion. And I get the current that I'm looking for in this case, and I get the voltage that I'm looking for in this case. So I hope this helped understand current division and voltage division a little bit more. One quick thing I wanted to mention about this way of thinking about current division is that it doesn't really work if you think about it in terms of resistances rather than conductance. And the reason for that is because, as I stated earlier, resistance is just 1 over conductance. So it's a really easy fix. If you have a bunch of parallel resistors, all you would have to do is convert them to conductances by taking the reciprocal. And if you convert all your resistors into conductances, then you can use this current division formula that I've made a little bit more intuitive here. Thank you. So the next thing I'm going to be doing is practice 3.17 from Engineering Circuit Analysis by Haight. And it asks us to find this current I1, current I2, and this voltage V3 using resistor combination methods and current division. And so the reason we can't use current division straight away here, and the reason is that we don't have it in the structure that we want for current division, and the reason, and that looks like this. So that's just one current supply and then a bunch of resistors in parallel, and we don't have that here because even though we have a current supply, we have R1 and R2 in parallel. We can't really say that any one of these single resistors is in parallel with R2, and for that reason we can't use current division straight away. But one thing we can do is simplify resistors, and hopefully we can get it into the format that I just had. And so the first thing I'll notice is that R5 and R6 are in series, and I like to write out all my values symbolically and then plug in numbers when I'm actually doing calculations. So the first thing we notice is that R5 and R6 are in series because the same current is going through both of these resistors. And so I'm just going to replace these two resistors with one series resistor, and I'll come back to V3 at the end. So I'll say that R7 is just equal to R5 plus R6, which equals 40 plus 20, so that's 60 ohms. And again, I'll come back to solving for V3. So I'm going to erase these two and replace it with one resistor, that's 60 ohms. And I'm going to label it R7. And the next thing I notice is that the resistors R4 and R7 are in parallel. And the reason for that is because they're connected to the same two nodes. So they're connected at this node here, and then at this ground node here. So since they're connected to the same two nodes, the voltage across them is the same, and I can combine them in parallel. So I'll say that R8 equals R4 parallel R7, and just using my calculator, that gives me a resistance of 48 ohms. So what I'll do is I'll remove these resistors from parallel, and I'll replace it with one resistor that's 48 ohms. So I'll just erase this right here. And I'll replace it with a resistor that's labeled R8. That's 48 ohms. Okay. And the next thing I notice is that this current I2 is actually going through both this 2 ohm resistor and this 48 ohm resistor. So I can actually combine these two resistors in series while keeping I2. So I'll say that R9 equals R3 plus R8, and that's just 2 ohms plus 48 ohms, so that's 50 ohms. So I can erase these two, but I can keep I2 because I2 is going through both resistors. So I'll replace it with a 50 ohm resistor with a resistance R9 and a current I2 that's going through it. And now we see that we have this in the right format for a current division, because we have one current supply here and then a bunch of resistors in parallel because they're connected to the same two nodes. So that means that I can actually use the current division formula to solve for the current I2. So one thing that you notice is that everything is given in terms of resistance. So I have 125 ohms, 50 ohms, and 50 ohms here. And so I can't exactly use the conductance version of the current division formula unless I converted everything to conductance. But since I'm just given the values in terms of resistances, I'll just use the current division formula that involves resistance. So I'm going to say that I2 equals my current supply, I, multiplied by, and since this is the resistor version, I flip the conductance version, so it's all the resistors in parallel, so Req, that this current source sees, the equivalent resistance. So it's just going to be R1 parallel R2 parallel R9, and all that over my resistor R9. So if I plug values in, I get that this is 120 milliamps times 125 ohms parallel 50 ohms parallel 50 ohms divided by 50 ohms. And if I plug that in my calculator, I get a value of 0.05 amps, or I2 equals 50 milliamps. So now that I solved for I2, the next thing I'm going to do is solve for I1 and V3. The next thing I'm going to do is solve for I1. And before I do that, I'm just going to label some extra currents, IA and IB, through the circuit that will help me find I1. And I can just write, the first thing I can do is I can actually write KCL at one of these points. And you can realize that you don't actually have to write KCL at a particular node, but you can just pick a point in a circuit where currents are flowing in and out, and you can write KCL because, again, charge has to be conserved, no matter if you're writing it at a node or just at a specific point in the circuit. So if I write KCL at this particular point, I can see that I1, which is the current going in, equals IB, which is the current going out, plus I2, which we already found. I'll write that here. So I2 equaled 50 milliamps. And so if I can just find IB, since I already know I2, I can just add them and find I1. So in order to find IB, I'm just going to use current division once more. So IB equals the current source I times all the resistors equivalent, so R1 parallel R2 parallel R9, divided by the resistor R2, because that's the resistor I'm looking at. And so if I plug numbers in here, I get that IB equals 120 milliamps times 125 ohms parallel 50 ohms parallel 50 ohms divided by R2, which is 50 ohms. And I'm actually going to notice that this is the exact same formula for the current IB that I had for the current I2. And you can see that if you just rewind the video a little bit. And so I'm just going to skip straight to the answer, which is 50 milliamps. For IB at least. And so I'm going to write out that IB equals 50 milliamps. And so now that I know the currents IB and I2, I can solve for I1. So that means that I1 equals 50 milliamps plus 50 milliamps. So that means that I1 equals 100 milliamps. So now that I have I1, the next thing I'll do is solve for the voltage of V3, which I initially erased at the start of the example. So the next thing I'm going to be doing is solving for V3. Now V3 is the voltage across R6. So what I can do here is I can try to see if there's any way I can use current division to solve for V3. And it's looking like this current supply is not in parallel with R6 ultimately, so I can't really use current division using this. But one thing I do notice is that I can actually use current division using the current I2. And the reason I say that is because I have a current, so first of all, this whole block here, it contains a parallel combination. And that's because R5 and R6 are in series, but R7, which is that combination, is actually in parallel with R4. And so R4 and R7 are in parallel. So I'll redraw that here. I'm just redrawing the right side of this circuit. So I have R4 and I have R7 here, which is just combining R5 and R6. And I see that these two resistors are in parallel because my ground node is down here. Another thing I can see is that I have a current I2 that's entering this top area and splitting between R4 and R7. And so since I have a current that's actually splitting between two resistors in parallel, I can use current division using I2. And that'll make a lot more sense if I redraw this part of the circuit like this. So I have a current supply kind of. Now this is not the actual circuit obviously, but this is just another representation with a value I2. So this value I2 is entering this area, this node here, and it's splitting between these two groups of resistors. And since I have that, I can actually use current division with I2 as my source voltage, even though it's not this initial source voltage. So I'll actually write the current, I'm going to make another current here called IC, and IC is just the current through R5 and R6. And I'm going to write out that IC equals, remember I said that I2 is my source current, which is so I2, and then since I'm just looking at this side of the circuit, I need to find the equivalent resistance that I2 sees. So I have I2 here, it's splitting between R4, and I combine these into R7. So the resistance that I2 sees looking from this side is R4 in parallel with R7. So I can write that up here. So R4 parallel R7, and then that's divided by the resistor that I'm looking at. And so since IC is actually the same current here, since R7 is R5 and R6 in series, IC is going through both of these resistors. So I can write R7 here. So just to recap, I simplified the right side of this circuit so that I2 is actually splitting between R4 and R7, where R7 is R5 and R6 in series. And so if I solve this out, I can find a current IC. So I get that, so IC equals I2, so 50 milliamps, times R4 in parallel with R7, so 240 ohms, parallel 60 ohms, divided by R7, which is 60 ohms. So I get that this equals the following. So I get that this equals 40 milliamps, or 0.04 amps. And the next thing I can do is, since I have this current IC, I can just use Ohm's law to find V3. Because for this resistor R6, I have a current IC, I have a voltage V3, and I have a resistor R6. So if I erase all this, I'll write out first here that IC equals 0.04 amps. So I get that V3, just using Ohm's law, equals IC times R6. And substituting values gives me, so IC, which is 0.04 amps, times R6, which is 20 ohms. I get that equals 0.8 volts. So I have my answers here. So I have that V3 is 0.8 volts. I have that I1 equals 100 milliamps, and I2 equals 50 milliamps. So I hope this video helped, and leave any questions in the comments.